last presentation of this session is going to be by Mike Anderson of Erthos on PV panel variability effects using PVLib.
Hi there. My name is Mike Anderson. How many of you have heard of Erthos before? A couple, more than I expected. So we're pretty new. Erthos, So Erthos is a little unique. We put panels directly on the ground, and most people don't quite absorb that when I say it first. We put our panels directly on the ground, in contact with the ground. And then the next thing people think is, wait a minute, what about soiling? What about flooding? What about temperatures? So rest assured, all those issues are either non-issues or they're solved. So one of the other consequences of this is we want to, well, one of the reasons we do it obviously is to remove metal, motors, trackers, to keep all the costs down. We also want to keep the civil work down. So we want to do no civil work. So we tend to follow the contours of the natural ground. And that's what I'm talking about here. If we're going to do that, we want to understand what are the impacts of doing that. Is it going to hurt our production? Is it going to be 1% less in production? And is it worth it to do grading to get that 1% back or not? Beyond that, if there's, we know it's got contour, is there a particular orientation we can put our plant to minimize that effect? So we wanted to evaluate this. We turned to PVLib. So this isn't, I'm not talking about Erthos here necessarily. What I really wanted to talk about here is how we used PVLib to solve this sort of problem. It's not a problem that many of you may solve, but it's an example of an interesting way you can use PVLib. So that's the focus. How did we use PVLib to do this? So the main calculation steps, I'm not going to go into all the details, but obviously we need the irradiance. So we can use PVLib to get that either for an example, for example, a clear sky irradiance in an afternoon, or using a whole TMY file. That's the GHI. We need to know the irradiance on every panel. So every single panel at the site might be at a different angle. So we use POA. We calculate the POA irradiance on every panel of our system to do this analysis. Then we need to know, and obviously the problem with this is the IV curves, the electrical mismatch. So that's what we're trying to solve for. So we need to generate the IV curves for every single panel. Then we need to, and a couple steps involved in doing that. We're using the single diode model that has been talked about here a couple times. Then we need to combine those together. So we combine those across each string, and then we get the IV curve per string. And then we combine all those strings together to get the IV curve for the entire system. After that, we know the IV curve for the entire system. We can get our max power point and compare that to the nominal value. So I'm going to go into a couple diagrams of how we go about that. So this is one condition, one position in time. And the main two things that we did with this study, we were varying irradiance and where the sun is in the sky, and the layout of the array, what's the variation of the ground that we need to follow. So those are the two things that I'm going to be changing throughout a couple of these slides. This example is a clear summer afternoon, so the summer is in the west, a little bit north of west. And let me direct you to the checkered box on the left, right in the middle there. That represents, it's a 27 by 30 array. That's our standard array, 27 modules per string, 30 strings, and our strings go north-south. So those colors, you can't see the color bar, you can't see any of these numbers, I know, but it's not important. The color bar shows the slope of each of those panels. So the slopes that we're varying go between 0 and a little over 8 degrees. It's kind of a design constraint for our systems. So all of those colors are within there, and in this simulation, I'm assuming just random variation, which is absurd, but it was just a kind of an edge test case. On top of that, the azimuths are anywhere, they're randomly distributed, -180 to 180. So that's the checkered box on the left. The checkered box on the right is the POA, so the irradiance on each of those panels, and it's similarly checkered. The white boxes are when the panels are more flat and the red and green are when they're more facing or facing away from the sun. So this is the simulation with those 27 by 30 panels. It's a little over 800 modules, 800 IV curves. I'm going to take you through the 4 plots there, starting on the bottom right. So we've seen plenty of these screens, so everyone's familiar with these. It's an IV curve. There are about 800 lines on there, 1 per panel. And you can barely see a blue line going through the middle. That's a nominal panel. That's the panel that's facing horizontally. So what we do is we take each module in a string, so we take 27 at a time, and we start adding up at a particular current, for example, current of 0, add up those 27, what is our resulting voltage, and then we go up to the IV string. So we keep doing that as we're stepping through the currents all the way up. So we would set up, in PVLib or in Python, we would set up just a linear, it doesn't have to be linear, but a linear variation of currents from 0 to our max current. And then we start stepping up that, adding up the voltages at each of those currents. And that's what gives us one of those IV curves on top. So we do that 30 times to get the 30 curves in the screen on the top right. That's the current voltage for the strings. And there are, we did that 27 times. So we get 30 IV curves for the strings on the top right. Similarly, to get the system IV curve, we would add up all of the, at each voltage, we would add up the currents and work our way across to come up with the IV curve on the left. And from that, we can drop down and get our PV curve and get our max power point. And you see the blue line for each of those. That's the nominal for each one of those cases. And then at the bottom, we've got the green and the red. The green is the nominal. The red is our situation that we're simulating. We get the 2 max power point differences, and I think that was about an 8% difference in this condition. And one thing I left out is the reverse condition, the reverse voltage situation. And if you look at I'm going to go backwards a little bit, you see the top of the red where it's the max power point. That's at about 1200 volts. And if you go up to 1200 volts and then over to the string IV curve, that happens, well, there's the 1200 volts there. And if you drop down, you can see, let me see if this cursor works. Yeah. If you drop down to this point, that point was over here. So that's where the max power point occurred, underneath this 1200 here for these situations. So once when we were moving up this way in our current to add up all the voltages, when we got past this one right here, well, we had to figure out what to do because that went to the left. And once it goes to the left, it doesn't just keep going. There's diode activation, reverse breakdown voltage that occurs out here. So it's going to go to some point and then it's going to stop. That information, so I just used this part of the curve in my analysis. There are other methods to take this curve and get the model out here on the left side, which I'm not pointing to this curve, I'm extending this one right here. But I didn't do that, I didn't need to do that. I simply extrapolated out to some voltage, some negative voltage of about 15 volts. And the reason that worked for me is because my max power point was always below where this started to occur. So over here on this curve, if I was wrong on that, that would have affected this part of the curve, but not my max power point. So just a warning, if you are doing this sort of thing, if you're looking at like heavy shading within your module and you have diode activation, you need to be more careful about this because that's going to be more significant. You need to account for that, but for this scenario, I didn't have to. And for all of my scenarios, I didn't have to. So this was just one scenario, pretty extreme case. A couple other scenarios I looked at. The number of scenarios are just infinite, the number of different terrains that you could have. But the top right, that's the one I just described. I looked at 2 other ones, kind of other unique ones. In each case, the strings go north to south. And this one I called the bilinear module distribution. So along a string, the modules, the terrain is sloping up and then back down. So there's a hump going east to west on this one. And so these panels, they're sloping up, they're sloping back down. And since this is the irradiance, since this is still a summer afternoon, the sun is up here, so these are higher irradiance, and these ones are facing away, they're lower irradiance. The other situation is what if the slope is running north to south, so the strings are in line with the slope. There's no variation in panel slope along a string, it's just between strings. So that's the bilinear string distribution, and once again, the sun is on the west, so these are seeing more sun than these ones. So those are the two other situations I looked at. Comparing those, I'm not going to go into a lot of detail on these, just to show that they're different, and we're going to get a different solution every time we have a different scenario. But for this one, since we have 27 modules in a string, we're going to end up, and it gets repeated. We just have 27 different IV curves here. And every time we combine it for the first string, we're going to get some solution up here. You see that dotted line barely? Well, when I do it for the next string over, I'm going to get the same solution. So all of these collapse to a common string IV curve. Oops. So when I combine those together, well, it's going to have the same shape as this one over here. And you can see in this situation, it's better than the random situation. This one's just a different scenario. Here, each module in a string is identical. So we also get a subset of just a smaller set of 30 IV curves here. And when we add each one up, we get a different IV curve up here, because this is, one of them is going to be along this string, the next one's going to be along this string. But when we combine them together, they have almost no effect on the final IV curve. And we get a solution for that. So if we look at just one of those, this is back to the original random panel generation distribution I was talking about. These are, instead of just 1 point, these are daily curves for just 12, the first of each month, just to see variation over the year. And a couple things to point out here. This is January. January had low irradiance, and it was a clear day, so there was a difference between the two. This is February, and it was a cloudy day, so you see there isn't much difference between the two. That's because the sky was diffuse. And if the sky's diffuse, it doesn't matter which way you're pointed. It's best to just be pointed straight up, right? You see more of the sky dome. So on cloudy days, it has less effect. On clear days, it has more effect. And then when you get into the summer months, it had an effect on the DC side, and I didn't go through all of those, the 4 items in the legend between AC, DC, but that's the difference here. These are the DC, and there's a little bit of a delta between the simulated and the nominal DC, but when you get to the AC, because it's clipped, there's no difference. So in clipped scenarios, we don't have a difference. So those were just different types of days that you might see. So we wanted to see what would the effect be overall over the entire year. This is a TMY file, and each of these values, it's the date, it's not the hourly values, it's the daily totals. And just looking at the top plot, these are the blue is the DC loss, the yellow is the AC loss. And so this is the loss, it's the performance difference between the simulated and a nominal if everything was just facing horizontally. And you see it's a higher percent loss in the winter months, and that's mainly just a function of dividing by a smaller denominator. But you do see some really low values here. Well, those are the cloudy days. The ones up here would be the clear days. And in the summer months, the loss gets smaller, largely due to clipping. If we use, this was the random panel distribution. If we use the other two scenarios, these plots would just look quite a bit different. They'd have very different behaviors. The overall loss on the DC loss was 4.3%. And I'm going to reference that on the next page, and this is the final page. 4.3%. So that was this point right here. So this was the random uniform generation at 8.6 degree random tilt variation. And so this was 4%. So there were a couple, the other three curves on this are not the TMY, they're just random days. So this is a clear sky summer solstice in the afternoon. This is a clear sky winter solstice. And this was the clear sky summer solstice in the noon, at noon. And a couple things to notice, well, this was the uniform random generation. This is the bilinear generation in the middle, and this is the string bilinear string situation on the right. For this situation, when we have the modules varying from north to south and going over a hump east to west, the type of day can invert. So here, this clear sky summer solstice afternoon has a lower effect than it did here. So some things may not be too intuitive. Once I was looking at this, it's like, oh, okay, that makes sense. But it didn't make sense until I ran the simulations. Here, the TMY is, it would be better if we had this situation than this situation in this location. The losses would be less. Here, I mentioned that I was using an 8.6 random variation. That's pretty extreme. You know, if it were 4% random variation, the loss would be on the order of 1%. So this was interesting to know that, you know, this was extreme. The kind of losses that we're looking at are probably on the order of 1, unless we had an extreme case. But if we wanted to improve that situation even more, if we look over here, if we were to, in a situation where we had a known variation, even variation, if we were to align our modules, our strings with the variation, then we can greatly reduce it in all situations. So this serves for general understanding of, you know, how big might our loss be. For design situations, if we have a site and we know that there's some sort of shape to the ground, we can orient the system to decrease that, the issues related to that. And for O&M purposes, when we're modeling, if we have the topo, if we do a LiDAR of the entire array, the entire system, we can use that with PVLib to actually model this, incorporate it, and get more accurate results. And that is all I had. Thank you.